Good afternoon, everybody, and thank you, Cypher, for this opportunity to speak here. I think afternoon sessions are always a little bit challenging to keep people awake, but there are not too many in the room, so I hope I can manage it. So today I would like to talk about artificial intelligence in autonomous mobility. If you look at the mobility sector, artificial intelligence is playing a very important role, whether it is in all the mega trends, whether it is electrified, automated, connected, shared, yearly updated. In all these spaces, it plays a very important role. So why is it very important? I would say that, if you look at the world scenario, every year we are losing around 1.35 million people in accidents. That's quite a big numbers. And on top of this, we also lose around we have 50 million people injured in accidents. So this is a large number, and one of the major drivers of introducing the autonomous mobility is safety. Yeah, and at Continental, we have a motto which we called zero vision, and that means zero accidents, zero fatality, zero injuries. That's what we work for. So, meanwhile, I would like to show you a video on how autonomous vehicles are going to be in the future. And I think that video will help you to give a preview of what I'm going to talk next. So this is not a fiction anymore. This is what we are working towards. And I'm sure that all of you who live in Bangalore would agree that it would be really helpful to have a system like this, right? Yeah, how many of you got stuck in the 3.75 lakh vehicles traffic jam which was there 2-3 weeks back? Then when you look at it, this is like, wow. Yeah. So just a little bit background on the autonomous mobility itself and what are the different functions that we have there. So what happens in the autonomous mobility space is that we are changing the responsibility from a human being into a machine. Yeah? So the first one, which is we have 5 levels of autonomous driving, which is L1 to L5. And when you actually move across L1 to L5, what happens is you have the first level, we have limited braking or steering. And the second one, you have the steering and braking, which is partly done by the machine or a little bit assisted by the artificial intelligence. And in the next level, we are talking about hands-off. You would have seen it. I mean, most of the stuff I'm talking about, you would have seen it in the video. You have the hands-off. And the next level is, which is very important, which we are trying to get there, which is minds-off. Yeah, minds-off from the driver's side. And the last but not the least is the driverless one. So what happens is the first level, the first and two, the human being is monitoring the driving environment. And in the last 3 levels is basically the automated driving system monitors the driving environment. So what's happening basically is that we are placing AI behind the steering wheel instead of a human being. Sometimes scary to imagine, even though I come from the automotive world, but I think that we will get used to it. So when you talk about the degrees of automation, in the level 1, I'm sure that in the Indian market itself, all of you are familiar about the cruise control, the ACC or the adaptive cruise control. That's one of the functions, what is commonly used. Coming to the second level, we are talking about partial automation, which is again the automated parking and the traffic jam assist, which you again saw in the video. The third one, which is conditional, which we are talking about, the driver can take the hands off and rely on the machine, and whether it is a cruising chauffeur or maybe a traffic jam chauffeur, this is something which can help. But this is not a scenario where the driver is not required. The artificial intelligence and the driver has to coexist and do things together. Level 4, which is high automation, yeah, where actually you can leave it to the machine, but you need always a standby as a driver. The cruising chauffeur and the valet parking, which you saw, the lady entering the number, the parking number in the phone, and then the car parks on its own. And last one is the full automation, which is the self-driving car. So autonomous driving is not something very new. It has been started in 1989. And at that point of time, there was a pilot which was done, which was using neural networks. But then, the processing power that we needed, the algorithm, there are a lot of things which was needed. And over a period of time, the last 30 years, there's a lot of evolution which has happened in this area. So now, when you look at the autonomous driving, what really happens? I told you that you are putting artificial intelligence behind the wheel. So what does a human being do when he or she drives? You have your senses, which is your, eyes and ears and everything, and you sense something. Yeah, then after that, when you see an obstacle on the road, you kind of process the information. So you're thinking, yeah, you have a perception of something, then you're thinking, and the last one is what you do, you act. So either you turn your steering wheel, or you accelerate, or you brake. I think there are different actions that we do when you're driving. So in the autonomous driving, when you talk about the function chain of effect, it is exactly the same thing. There is no difference, except that it is done by, you're trusting the machine to do it rather than the human being. So when we talk about sensing, what are the important things that replaces our eyes and ears and other sensors? So we have cameras, which is all around, yeah. And then we have got radars. Then we have got LIDAR. LIDAR is nothing but it's something which actually detects the distance it detects the obstacles mainly by using laser beams. And then you also have a lot of ultrasonic sensors. So I'll come to a little bit in detail. And then you have all this data coming in from all these sensors, so you need to make sense out of it, right? So the first thing what happens is you do a lot of image processing with that, and then we also do a lot of object detection and tracking. And the first important thing is to find out where the vehicle is. So localization of the vehicle, where the vehicle is located correctly at that point of time is very important, and that is why we need a lot of high definition maps for that. And then once it is done, since you are getting signals from the different sensors, you need to make sense out of it. So, you have the camera signals coming in terms of pixels, and we have the radar signals coming in and LIDAR, and you try to fusion these data, and that actually gives you much more accuracy. And then you start thinking. That's the planning part, right? So you have sensed, you have perceived, and now you start thinking, hey, what's the situation? What can I do to my car? Should I turn the car? Should I stop? Should I slow down? Is a pedestrian crossing the road? So all kind of things comes at this point of time. And then you have something which is called actuating, where you either turn, you brake, or you control the powertrain, which is actually, controlling the acceleration of the vehicle, and also maybe you look at the HMI. Sounds very simple when you explain like this, right? But in terms of the software, if you have to implement it, it is pretty complex. Yeah. So I will tell you what are the reasons for this, the complexity. So let's talk a little bit about, you can also see where the sensors are in the car. In India, we have up to L2 now. Yeah, you have two of the OEMs in India looking at, the L2. But L3 is yet to come. L2 plus could be a parking solution. Maybe Tata would introduce it in the next couple of years. So we have satellite cameras, smart cameras, and you have two types of radar, which is the long-range radar and the short-range radar. LiDARs are very useful, but at the same time, LiDARs can never detect long distances. So we have a limitation of the distance which is there. And so this is how it is actually positioned. And of course, we have something called an ADCU, or an automated driving control unit, which actually does all the processing. So you have something what we call as a function chain of effects. You can see the, let's take only 3 sensors now, just to get a little bit of clarity. So you have the LiDAR. So the LiDAR will actually detect where the object is, and it kinds of a spatial information of an object. Then you have the camera, very simple. It is in terms of the megapixels, that you generate. And then you have radar, which is the distance of the object as well as the moving speed of the object is detected by the radar. So why do we need all these sensors? Doesn't it make it expensive? Yes, it is because all these sensors have limited capability to act upon, and you need the complementing powers of these sensors to take it forward. For example, if you look at a camera cannot see very well when you have rain, fog, and so on. So that time, it uses the complementary skills of LiDAR, so the radar and LiDAR. And LiDAR at some point of time, because of the laser detection and other things, you can get a 3D information, but some other information is missing. So you always use a combination of these things, and there are 3 levels of fusion that can happen here. One is the low-level fusion, which is just bringing the things together. And in the mid-level fusion, where we talk about the feature detection. So feature detection is what? It's pretty simple. When you talk about the road, let's assume when you're driving, you have different objects on the road. You have pedestrians, you have cyclists, you have other cars. You may have vegetation on the road. These are all things where probably the car has to stop. Then you have some things which can be misleading. Like you may have dirt on the road, which doesn't have a dimension, but you have a color there. Camera could detect, but it doesn't give you the spatial information. So there is, if you just imagine the road scenario, maybe we are so used to driving, we don't think about it, but from the machine point of view, it can be quite complex. So what is important is what we call as the tracking and the environmental modeling. And the environmental modeling is nothing but you kind of create a digitized version of the surroundings of the vehicles so that you can act upon it. So that's what we call it as CEM, Comprehensive Environmental Modeling. And then based on the output of that, you have a lot of here, this is where a lot of artificial intelligence come to place. And you have different algorithms, different methods that we use. For example, when we talk about the mid-level fusion, we also talk about something called a bird's eye view, where the 3D also comes into picture. So different types of algorithms are applied, and different AI methods and deep learning is applied when it comes to the sensing part. So this is one part, and then if you look at it, if you can just see here why are complementary sensor technologies and fusion required. Each of these sensors are also assisted by AI. You have ground obstacles, you may have to take a different way. You have complex and dense traffic. It can be a little bit, again, complicated. Lighting condition, if it is a blinding light, the camera cannot detect it like in the same case of fog and rain. Then you have pedestrians. You may have actually dummies and pedestrian not moving. So you may have somebody who's waiting at the zebra line crossing, but maybe it is a dummy, it is not a pedestrian. So it is really difficult for even the car or the AI to judge whether it is a pedestrian. Second thing is we have something called, vulnerable road units, which is, these are people, cyclists, whatever, we don't know what they do next. They are standing there, will they jump into the road, will they stand there? Very difficult to predict. And then you have lateral entry of vehicles. In India, amazing, right? So this is a very interesting use case. And even the VR use, the things like cow crossing the road and things like that are difficult to implement in the algorithm, which means that we need to train the models again and again. The real life scenario, the training in real life is quite difficult because we are talking about a safety critical application. And adverse weather I already mentioned about. So when you talk about the sensor building blocks, you can see that in the diagram you can see camera, radar, lidar. So each of it has got its own detection capability. For example, the road semantics and the object detection for color, the size, the edges, and all that is very interesting for the camera to pick up. Then in the case of radar, we have the weather robustness, the velocity, and so on. And in lidar, we have got a 3D point cloud, the road surface, which is the spatial information. So each of these sensors are used, and that is why you need the sensor fusion to move forward. So now when we look at the environment model, as I mentioned, it is nothing but it is a digitized version of the surroundings of the car. It is not only enough to have sensors around the car, we also have to have sensors in the car. That is because we are also monitoring, in the autonomous driving, it is also important that we monitor the passengers. For example, if somebody has not worn a seat belt, we need to track that and then alert it, right? So that's one maybe very simple use case. But we also have, how is the alertness of the driver? So there is something which we call as FMS, which is a fatigue monitoring system. Is the driver tired while using? Because if the driver is tired, there is every chance that you have an accident. It has a direct implication of safety. So in the FMS, what happens is there are multiple parameters that are monitored. So one is, is he steering properly? If the person is sleeping, sometimes, how he steers the vehicle changes. Then they monitor how is the eye position. Is it closing, opening, drowsy? They look at the shoulder position. Is it stooping or the person sitting straight? Then they also monitor looking at, how long the person has been driving. What is the time of the day? Has he had a meal before driving and so on? So there are multiple inputs that goes into an FMS. And the AI models actually predict whether the person is sleepy or not, and it can actually give warnings either in terms of a bus or an alert or a warning so that, they can actually decide the course of action. So in an environmental model, for example, there are different ones. One is the object detection. We have got features like emergency brake assist. You would have seen that, when a vehicle is approaching and you are maybe crossing the road, then you have an E-bar, we call it an E-bar. And you need to either slow down or stop. It again depends upon what is the distance that you are there, what is the, where the object is placed, and there are other conditions which you look at it. Similarly, traffic signs, traffic light detection is also something part of the object detection. Then when it comes to the camera, there's something which we call as again semantic segmentation. This is every pixel of the camera is put into a class. And what is a class? A class is nothing but you can tell that the class can be one type of class could be maybe a tree or vegetation. One class could be pedestrian. So there are different classes which are occurring, and every pixel what the camera picks up, it actually is moved into one of these classes, and that's what is used in semantic segmentation. And when we talk about automatic parking and parking space detection, these are some of the techniques which are used very widely. Another one is lane detection. I think when you are actually driving in a driving in a highway and you have your ACC or the adaptive cruise control on, you may have a turning which is coming in. So actually you need to know whether you are really going on track or not, and then you need to have different kinds of warning system which will help you. And last but not the least is the human pose estimation inside the car, outside the car. As I mentioned, VRU is nothing but these vulnerable road units, can be pedestrian, cycles, etc., where we can't predict what they will do next. Anyway, no human beings we can predict, that's a different story, but in terms of driving it makes a lot of difference, yeah. So, so object detection, traffic light, and these, I think you can see, and if you see each of these things, I'm not getting into detail because of want of time, each of these have different algorithms behind it. For example, object detection is normally you have the CNNs and SSDs which are supporting them. And when we have maybe a lane detection and tracking, we have a Kalman filter and the RNN-based systems which are coming in. So which means that the amount of technology that goes in behind each of this is huge. And you can also imagine the data that comes from each of the sensors. Yeah, I will take you through a slide which talks about what kind of data is generated per minute from a radar, from a lidar and camera. It's really mind-blowing and unimaginable amount of data. So it can also have applications in free space detection, seeing the lost cargo, and each of them have different sensors which are possible and the different algorithms which can be used for it. So now when you look at where is the classic machine learning coming into picture and where is deep learning coming into picture. So in the older versions, we were actually using only the classical machine learning along with computer vision. Computer vision is it's a part and parcel of the autonomous mobility. And in this case where we are using the classical machine learning, basically we were looking at extracting the features, just the features, and the features are something which is defined by a human being. So which means that accuracy again depends upon how the features are being fed and how it is being defined. So when we talk about the machine deep learning, which actually brings in much more accuracy into the system, you are allowing the system to learn on its own, and it's a kind of an end-to-end learning that is happening. So let me give an example. So let's assume that using the first step that you are identifying a cat. Yeah, so more than a car, let's take a cat, much more simpler to look at. So maybe in that case, you will tell in the first case, you will tell the features. You tell, okay, it has got ears, it has got nose like this, it has got whiskers like this, and then you try and define that it's a cat. But what happens in the deep machine learning, in a simple terms, it is like you will feed it thousands and thousands of photographs of a cat, of many, many cats, and then the machine will learn by itself and then start defining that, hey, this is a cat. So that's basically the difference. But in the second one, since it is not fully defined and the feature is not defined and given, the challenge is that it also consumes and requires so much of data, because that is what is required. And when you talk about a car, you also have the control unit. The amount of computing power that is required for this is also pretty much huge. So just maybe you can just go through, you can see how, the camera, radar and lidar, does it. It is just a simple thing like a detection of a pedestrian who is standing near the zebra crossing. So first of all, the car has to know it is a zebra crossing. Then it has to see what is the distance, is he moving or not. You can see one leg up. So your assumption is that probably he will keep the next step onto the road. So here you use the segmentation of the camera. Every pixel you classify and then you find out that it is a human being. Then you also look at what kind of optical flows which can happen. Again, we use a lot of sensor fusion into this technique. And then you also look at the depth of the object. Is it a dummy standing there lifting a leg, or is it a human being? You also have to look at what kind of depth will come into the system. So this is maybe in just detecting a pedestrian. So you can imagine maybe in Bangalore traffic, if the car has to go, what kind of stuff it has to detect. So so this is one part which we have to do. The other thing is, if you look at the autonomous mobility part, even not in the autonomous, even for the normal cars, there are different use cases which we can use artificial intelligence. So one is the parking assist. I think you can, get out of the car, ask it to remotely park, or maybe you sit inside the car and you look at left, right, and use the patterns to do that. Then we have in-cabin sensing. I mentioned already about the drowsiness of the person, looking at the angle and so on. And one more new topic which is coming up is the health monitoring. I think that is coming up very much after the COVID, that a lot of people are suffering cardiac arrest during driving. So now the OEMs are really asking for some mechanism by which you can have something on the steering wheel which can detect the blood pressure and the heart rate and other things and give a predictive warning. So here again, the predictive algorithms come into play. So this is something which is, many of our OEMs are asking us, can you design something like this? And also using thermal imaging techniques to also protect the health of the, I would say, the riders behind also. So that is another thing which is again using artificial intelligence. Emergency brake assist also has artificial intelligence. And when we talk to even safety features, like for example, you have maybe a car and you have a family of 3 people who are using the car. and each of you will have different AC settings you might like. Each of you will like a different infotainment channel. Yeah, and each of you will have a different steering column adjustment. So what happens is, when the person uses biometric and then you open the car, that time itself the car arranges itself in such a way that these settings are already there before you getting into the car. That's another use case which is simple, and we use AI in these features also. Similarly, while driving, maybe it is mid-noon, and the car can give an alert telling that it is mid-noon and you may be hungry, so do you want to stop at the next pizza stop? So what happens is, it already stores what is the kind of food the person has had. It already stores what was the lunchtime, the normal lunchtime pattern of the person, and then gives the indicative. Similarly with insurance, now we have insurance premiums which are coming up with the driving pattern. If somebody drives rashly, you have to pay more premium. So that's also coming in. So if you have any rash drivers here, beware. Maybe something will come soon and you may have to pay extra premium. So similarly, these are some of the things, many use cases which we have in the industry at this point of time. But what is very important is that, the car has only, any car or, whether it's a truck or whatever, any vehicle has got only very limited processing capability. And you need to move a lot of this computation into the cloud. That's very important. So just look at the flood of data which comes in the autonomous mobile. For example, a radar can generate 10 to 100 kilobytes per second. And if you're talking about a vehicle which is running maybe 8 hours, 9 hours, if you're driving, just imagine the data is churned out. Similarly, cameras, again huge, it talks about 20 to 40 MB per second. It is a lot of data, and which means summarizing an autonomous vehicle could have around 4,000 GB of data per day, each day. And then you need 5G to transfer to the cloud. If you want to transfer 1 day of data according to a normal Wi-Fi speed, you can imagine how many days it will take. But that is why 5G and any faster communication is also helping the autonomous mobility to move forward. So when you look at it in the mobility industry now, it is a kind of all complementary technologies coming together, which is artificial intelligence, which is data analysis, which is 5G, which is augmented virtual reality, and all these technologies have to coexist if you want to have the complete autonomous mobility a success. So challenges, what we have, one is a self-driving cars cannot be trained real life. You can imagine none of you will be ready to be a pilot there or a guinea pig there. Very unpredictable human or cattle behavior on road, even other vehicles. The algorithms what we have at this point of time, they are not mature and optimal to perceive the road and the lanes what we have in the different parts of the world. And then, if you look at the optical sensing modality, whether it is mapping part, whether it is localization, all of them still lacks accuracy, and we can't play with human life. So that's something where AI is also playing a very important role. The algorithms are getting matured, deep learning is getting matured, and we need to have high-end processors which can actually support it. V2X is still a dream because infrastructure, when we talk about it, vehicle-to-vehicle communication, vehicle-to-infrastructure communication, especially when we talk about a country, it is still a long dream, I would say. And cybersecurity, because we are talking about data, and the vehicle is currently, any car which we can call it's an IoT connected to the internet permanently, right? So that's something very important. Cybersecurity is important. Okay. So summary, I would say that in all autonomous vehicles, the key is safety and comfort. And if you look at the new gen, everybody looks at having comfort and convenience more than safety. But the thing is that it is important to look at safety aspects first. Right, thank you. So there are 3 critical steps I mentioned in the whole process. One, it is sense, which is using the camera, radar, lidar, and the other sensors. And then we have the plan, where we use a lot of artificial intelligence, what to do with all these sensor fusion and semantic segmentations and all. And last but not the least here, act with the actuators, which is steering, brake, accelerator, and so on. Complementing sensor technologies and sensor fusions are really required if you want to use AI in a much better way. And the synergies of technologies have to be used, whether it is deep learning methods, whether it is CNN, and any other algorithms which are there, we need to have these kind of synergies of multiple technologies, multiple algorithms coming, as I showed in one of the slides. For each of the applications, you have different algorithms coming into picture. And we also need to have further optimization of AI because we are talking about safety critical application. And that's where the industry is. I would say that in the last decade, we made tremendous amount of progress in the AI space. But I would say that it's still got very high potential, at the same time high uncertainty, because finally we talk about vision zero, which is zero fatalities, zero zero accidents, and we need to save life. So thank you very much. I would like to conclude by telling that the greatest danger that I see with artificial intelligence is that we are concluding too early that we are understanding it, and I'm not sure are we really understanding it or are we even underestimating it. Thank you very much.
Hello. So here you have mentioned about moving the data into the cloud and about something 4,000 GB data, something. So, but my question is, instead of moving to cloud and then getting the response like 5G or maybe 6G also, it will be challenged. So why can't we run algorithm on the edge in the vehicle, and then it will, this algorithm will detect, and then it will give the signal, okay, go, stop, like that?
We use a combination actually. All the critical algorithms are run inside the car itself, and that is why from the standard ECUs what we have, we are moving to the high performance computers. So in the normal vehicle, if you look at it, we have HPCs, the high performance computers. We have also called zone control units. So a lot of power is already in the vehicle, and we try to use that. But there are some things which is not time critical, to respond, and other things we put it into the cloud. So it's a combination of both. You can never get rid of the processing inside the vehicle because it has to be very fast.
Okay, yeah. Thank you.
Latha ma'am, I have a question. Yeah. So in terms of training the models that are running in the autonomous vehicles, why do we not create a system that could be retrofitted in the car in the current state itself, which has all the sensors, and the pilot behavior is monitored right now, and that itself trains the model, and eventually it goes out as a proper standard. I mean, you could take this pre-trained model out and then put it in the car in the future. So have we not thought about scenarios like this?
It is not very simple. We also do that. For example, we have a data center in Whitefield, where we actually collect the data and we are processing, we are creating the models. But what challenge is that still is the moving target. You get a lot of, because when we are talking about deep learning, the more data you get, the more accurate it is. And as I mentioned, all the algorithms are still not mature to a stage where we get so much of accuracy. So you need to do a combination. Yeah, so the data center actually hosts, many petabytes of data, and then we do modeling with that. But that only covers some scenarios. And when you just imagine, just imagine the ring road and then check, that kind of scenarios, if you have to create, the amount of data that we need is really huge.
Yeah. I have a question. I would like to know your views on the software 2.0, which a word coined by Andrei Karpathy, in which he argues that perception, planning, and control, everything put together goes into a single model, and there's no software working as such. So your views on software 2.0, and if it is here to stay and this is the future, and will it also go to other systems like BCM and beyond autonomous vehicles, other controllers in the car?
Too early to tell now, because I think it's in preliminary stages, and our organization, we have started looking to it, but I don't have the know-how to tell you that what course it will take, because we have just started it. Yeah, so no more questions. Thank you. Thanks again for the patient listening.